In this video, we'll go over the homework that follows the lecture on Introduction to Taylor and Maclaurin Polynomials, and as always, I hope that you watched the lecture before attempting the homework. And let's go ahead and take a look at the first part of the homework, and we are asked to write a polynomial representation of or approximation of a given function. And in this case, we're talking about Maclaurin polynomial. That means we are centered at 0, and we have to find Maclaurin polynomial of degree 2. And there are two ways of doing it. One is to pretend that you don't have any past knowledge, and then find the coefficients of the polynomial using this formula. So in such a case, we have f of x to be e to the power 2x. So f of 0 will be e to the power 0, which is 1. So a0 is equal to f of 0 over 0 factorial, which is 1 over 1, 1. F prime of x is 2e to the power 2x. So f prime at 0 will be 2. So a1 is equal to this, so it's 2 over 1, so it's 2, and then the second derivative is 4e to the power 2x. The second derivative at 0 is 4e to the 0 which is 4. And a2 is equal to the second derivative at 0 divided by 2 factorial. So it's 4 divided by 2, which is also 2. And now putting it all together gives us the following polynomial. And the reason why I call this an approximating polynomial is because if you actually graph the function, and then you graph this polynomial, you're going to see that this polynomial approximates this function around 0 very well. So that's what it means. Now, alternatively, we can find this polynomial by starting. So we have f of x e to the 2x. And we're going to recall that e to any power is the same as so if we let the star to be equal to 2x, then e to the power 2x is equal to this. And this is known as Maclaurin series for this function. And to obtain the Maclaurin polynomial of degree 2, we just have to evaluate this for n equals 0, 1, and 2. So when n equals 0, we get 1. When n equals 1, we get 2x, and when n equals 2, we get 4 divided by 2 factorial, which is 2. So there is more than one way of answering this question. So here's the answer: 1 plus 2x plus 2x squared find Maclaurin polynomial. Similar problem, and by now you can develop a preferred way of finding the Maclaurin polynomial. I'm going to use the series. It is a more powerful way, so we're going to recall that cosine of something is equal to -1 to the power n, x to the power 2n minus 1 over, actually there is no -1 there, 2n factorial. And now if we let the star to be x over 3, then cosine of x over 3 can be written as the following series. And it can be simplified so I have -1 to the power n, x to the power 2n, 3 to the power 2n, 2n factorial. So to find the polynomial, Maclaurin polynomial of degree 2, means we're going to truncate this series and only keep the first 3 terms. So 0 power first and second. So when n equals 0, we have we literally have 1. When n equals 1, we have minus. We're gonna have x squared, and we're gonna have, well, actually in this case, because the powers are doubled, we don't have to evaluate it for n equals 0, 1, and 2. The first power is going to be missing pretty much. And here we have 3 squared times 2 factorial. So again, to check your answer, you can always just graph, just to see what's going on. And what we're claiming here is that this polynomial (3 squared times 2 factorial) something's not right here. Hold on. Where's the red function? Oh yeah. Oh my god. The approximation worked so well that I didn't even realize the red function was behind the blue one. This is exactly the purpose of Taylor and Maclaurin polynomials. So the answer is 1 minus 1 over 18 x to the power 2. Here we're going to use the formula. So P2x, actually P3x will be A0 plus A1x plus A2x squared plus A3x cubed, where A sub n is the nth derivative evaluated at 0 divided by n factorial. And we're going to start with f of x, and f of 0 is 1, so a0 is equal to 1 over 0 factorial, which is 1. Now the derivative is the derivative of this is 5 to the power x times ln 5, so f of prime of 0 is ln 5, so a1 will be ln 5 divided by 1 factorial, which is ln 5. The second derivative will be 5 to the power x ln 5 squared. Evaluating it at 0 gives us ln 5 squared. So the second coefficient will be ln 5 squared divided by 2 factorial. The third derivative, I guess we can see the pattern here. So the Maclaurin polynomial of degree 3 is 1 plus ln 5 times x plus 1/2 ln 5 squared x squared plus 1/6 ln 5 cube x cube. And we can do some properties here, so doesn't. I'm going to write it in exponential form. Makes it easier to find the derivative. So the derivative will be negative 1 to x plus 3 to the power negative 2 times 2. F prime at 0 will be negative 2 over 9, and a1 will be negative 2 over 9 over 1 factorial, which is negative 2 over 9. The second derivative will be 4 times 2x plus 3 to the power negative 3 times 2. The chain rule, the second derivative at 0 will be 8 over 27. So the second coefficient will be 8 over 27 over 2 factorial, so it's 4 over 27. The third derivative is negative 24 2x plus 3 to the power negative 4 times 2 by the chain rule. The third derivative evaluated at 0 is negative 48 over 81. So A3 will be equal to negative 48 over 81 divided by 3 factorial, which is 6. We can reduce it, negative 8 over 81. And the polynomial is this: 1/3 minus 2/9 x plus 4 over 27 x squared minus 8 over 81 x cubed. And before we enter this answer, we can check the intuition. So let's just graph the function and type this polynomial. And again, we're looking around 0, and it looks like around 0, the blue curve, which is our polynomial, approximates the red curve very well. So we can type the answer now. I wonder if I can just copy and paste it. If I can do that, that's just one more reason to check your working Desmos before entering the answer here. Oh, why? Oh, there's a 7 over here. Where did that 7 come from? Oh boy. Let's fix it. So we have 7 here. So that 7 means we have 7 here. That means we have 7 here and here. So we have negative 7/9. Now we have negative 7 times negative 2, that's 14. We have 7 here, 7 here. So we have 14 times 7 is 98. And we have another change here. So 14 times 7, it's 98. 98 times negative 3 is negative 294. So this is 7. I have another 7 here. So it's going to be negative 294 times 7. We're going to be changing this. Negative 294 times 7. It's negative 2058. Negative 2058 divided by, is it divisible by 6? Oh yeah, so we get negative 343. So let's just update all the coefficients. 49. Yeah, so let's check once again. And notice how, as we're changing the coefficients, the graph will adjust to match the shape. Right there. So let's now copy it again. And this time we got it right. So this was the first part of the homework. And now let's go to the second part of the homework. And in this part, we have to construct polynomials, Taylor polynomials. And the first problem is given this function. We're trying to construct a Taylor polynomial centered at x equals 6. So what does that mean? That means we're looking for a polynomial like this. And the coefficients can be found using this formula. And let's start. So here's the function. And we're going to find the derivative. And the derivative is 8/3 x to the power negative 2/3. Actually, that would not be the first step, but the second one. The first step, we have to evaluate this function at 6. So we have 6 to the power 1/3. And the zeroth coefficient is equal to exactly that. Now, the second step is to find the derivative, evaluate it at 6. So we get 8/3, 6 to the power 2/3. And the first coefficient will therefore be 8 divided by 3, 6 to the power 2/3. Now we find the second derivative. It's going to be negative 16/9 x to the power negative 5/3. Evaluating the second derivative at 6 gives us this. So the second coefficient will be this derivative. But half of that we divide by 2 factorial. Continue with the third derivative. We end up with 80 over 27 x to the power negative 8/3. Third derivative at 6 will be 80 over 27, 6 to the power 8/3. So the third coefficient will be 80 divided by 27, 6 to the power 8/3. But here we also have 3 factorial, which is 6. So the polynomial, the Taylor's polynomial of degree 3 here will be this. And in applications we would normally estimate all of these inputs. And write them in decimal form, so that I guess here we can reduce. Here's the same thing. We're going to reduce everything by 2. We have 81, 6 to the power 8/3, x minus 6 to the power 3. So that's the answer. Newton goes an extra mile to simplify each of these expressions, but we don't have to. Alright, so we have f of x is equal to 5x to the power 1/4 at x equals 5. And again, we're looking for P3. P3 will be a0 plus a1 x minus 5 plus a2 x minus 5 squared plus a3 x minus 5 cubed. And we're going to use this formula. So let's start. We're going to have f of x, 5x to the power 1/4. So f of 5 is 5 times 5 to the power 1/4, which is 5 to the power 5/4. And a0 will be equal to exactly that. Now, derivative of this is 5 times 1/4 x to the power negative 3/4. So evaluating derivative at 5, we get 5 times 1/4 times 5 to the power negative 3/4. So it is 5 to the power 1/4 over 4. So a1 will be that. To find a2, we find the second derivative. So it's 5/4 times negative 3/4 x to the power negative 7/4. Evaluating this at 5, we get negative 3/16. 5 to the power 1 minus 7/4, so it's going to be negative. I'm already like simplifying this, I guess, too much. So it's going to be negative 3/4. So a2 will be half of that. So it's going to be negative 3/32, 5 to the power negative 3/4. Now the third derivative is we have negative 15/16 times negative 7/4 times x to the power negative 11/4. Evaluating the third derivative at 5 will give us and a3 will be 1/6 of this, because we have to divide by 3 factorial. We can reduce this by 3, and we can reduce this by 2, multiply this by 2. And that's pretty much it, right? So my polynomial will be equal to 5 to the power 5/4 plus 1/4 times 5 to the power 1/4 x minus 5 minus 3 over 32 times 5 to the power negative 3/4 x minus 5 squared plus 35 over 128 5 to the power negative 11/4 x minus 5 cubed. And it's not pretty, so now we just have to type it all up. We have 3 times 5 to the power negative 3/4 divided by 32 x minus 5 squared plus we have 35 times 5 to the negative 11/4 over 128. I don't know, let's see. Very similar problem. The function is this. The center is at 3. So to find P3 means to find this polynomial. Where each coefficient can be found using this formula. So the first one we find by simply plugging in 3 for this function. So a0 is 5 times 3 to the power 1/3. Derivative of this is 5/3 x to the power negative 2/3. So the first derivative evaluated at 3 is 5/3 3 to the power negative 2/3. So a1 is equal to that. We can write it like this. The second derivative is now negative 10/9 x to the power negative 5/3. So the second derivative evaluated at 3 is negative 10/9, which is 3 squared, 3 to the power negative 5/3. So a2 is equal to half of that, according to the formula. So it's going to be negative 5, 3 to the power 11/3, and finally the third derivative is 50 over 27 x to the power negative 8/3. Evaluated at 3, we get 50 over 3 cubed, 3 to the power negative 8/3. So 8/3 is equal to 50 times, it's actually 1/6 of that, right? So we're gonna divide this by 2, and we're gonna add another power to the 3, so it's gonna be 3 to the power 4 in the denominator, and it's gonna be negative 20 over 3. So the polynomial is equal to 5 times cube root of 3 plus 5 times 3 to the power this is actually negative. Yes, it's not pretty, but it is what it is. 5 times 3 to the power 1 over 3 plus x minus 3, so negative 5 here, minus squared plus 25 negative 20 over 3 x minus 3 cubed. I think this was problem number 7. So this is 6. This is 7. And this is 8 now. So we have a function 3 cosine 2x at x equals pi over 3. We're trying to find P2. P2 will be equal to a0 plus a1 x minus pi over 3 plus a2 x minus pi over 3 squared. And in this polynomial, each coefficient can be found using this formula. And to find the 0th one, we start with the function. We evaluate the function at pi over 3. So cosine of 2 pi over 3 is negative 1/2. So the 0th coefficient is negative 3/2. Now let's take the derivative. It's going to be negative 6 sine 2x. Let's evaluate the derivative at pi over 3. Sine of 2 pi over 3 is root 3 over 2, so we have negative 3 root 3. So a1 is equal to negative 3/2 of root 3. Now let's do this one. We have negative 18 cosine 2x. The second derivative at pi over 3 is, so it's 1/2, again, negative 1/2, negative 18 times 1/2, so it's negative, so it's 9, and a2 will be this divided by 6 factorial, so it's going to be 3 halves. Not 6 factorial, 3 factorial, which is 6. So our polynomial looks like this. It's negative 3 halves, negative 3 halves root 3 x minus pi over 3 plus 3 halves x minus pi over 3 squared. And this is something that we can actually play with here, so we can graph it. So let's graph 3 cosine of 2x, and let's take a look at the graph of this function, but we're looking at pi over 3. So at pi over 3 will be somewhere right over here. And now we're going to sketch this polynomial. It's negative 3 halves, negative 3 square root of 3 over 2 x minus pi over 3 plus 3 halves x minus pi over 3 squared. Doesn't look good. Oh my god. 6 times 2 is 12. So there is no 18 here. It's 12. So there is no 9 here. This is 6. So there's no 3 halves here. This is 1. So this is 1. Still not correct. So I'm definitely not entering this answer yet. Need to fix my coefficients. Let's check again. Cosine of 2 pi over 3 must be negative 1/2. Cosine of 2 pi over 3. It is. Sine of 2 pi over 3 must be negative. Not negative, positive root 3 over 2. Oh my god. So again, we're not dividing by 3 factorial here, we're dividing by 2 factorial. And here we're not dividing anything at all, so this is the coefficients. So there's no 2 over here, and there's 3 over here. So let's check that. And there you go. Now you see how beautiful it looks. So that's the right answer. And we completed this homework. If you have any questions, feel free to reach out.